We have the honor again to have Luciano telling us about the charm Tau factories. Luciano, welcome. You can share your slides. They were up, but somehow they went off.
Oh, did he disconnect?
Maybe.
Uh-oh.
Are you there, Luciano?
Yes, yes, I'm here.
Okay. So you can just share your slides and start, Luciano.
Yes, let me go to my screen and share the light. Wait a second. Dunque, where is it? Sorry, I don't find this. Sao Paulo.
Maybe tetraquarks don't exist. No, no. Sorry.
Okay.
Tetraquarks disappeared. Oh, they're back.
Can you see it?
Yes.
Yes.
Can you see it now? Hello? Can I go?
No, wait.
They somehow became black. We saw them for a moment, but now they are gone. Oh yeah, it's like it's kind of weird because it seems like it's if you move something, they appear and they just flash.
What should I do? Start?
Maybe if you don't share the
Wait a second. I have.
just show them in your yeah.
I don't hear you well. Okay, tell me what I have to do.
Just start. We can see the slides. Like
Just start. You hear me? I can start. Okay, so it's a pleasure to be with you, and you see that.
All right. It's when they push the play button that they disappear. So maybe you just leave them there.
Yeah, don't push
without
the
play button.
Sorry, I didn't get what you said. You don't see the slide?
No, the moment that you press the play button to show them in full screen, that's when we don't see them, but we can see them before. So maybe you keep them there.
Okay, yeah. Wait a second. I can do perhaps something better. Now, let me do this. And now I share. So I share the, okay. Now I can open this. Can you see now? And open.
No, we see your screen. Only your screen with the folder, but not the not. So Luciano, I tell you what, yes. We have your PDF here. So is it okay if we?
Why? Why is it? But to say, I have opened it. I shared the screen. And
yeah, so we can. So what we can
see the screen now. Okay, so I can open that, but you don't see it.
No.
How can I do that? I can now. Wait a second. Share. I
we have this file against share.
Yeah.
Maybe we can drive from here.
Now I shared. Now I don't see anything. Can you show me the what you see as you did before?
Yeah, you. We see you.
You see me. Okay. Let's see if I can
So Luciano, we'll do it from here, okay? Is that okay?
Yeah, do it from there. It's much better. Yes, sorry.
Just 1 minute. Because you send the file, so we have it here.
You use the file that I sent you. Okay, now I see it.
Yes.
Can I, and then how can I go on?
So you just say.
Oh,
you want
okay.
to-
I
you
just tell you go on. Okay, okay. So go back.
Just
Go
1 second.
Now, go back.
We will go back. 1 second.
Okay.
Yes. Yeah.
Okay, so I will start.
Yes.
Okay, so this is just to recall you that 20 years ago, around 2003, the X3872 has been discovered, and then later more hadrons have been discovered, which cannot be described by the Gell-Mann used setup Q bar Q mesons and 3 quarks baryons. Next slide. Still, this is an old slide of Steve Olsen that shows in yellow the known charmonium states, and mixed with this spectrum, and in green the charmonium states predicted but not yet discovered. But mixed with the yellow, there are new states which appeared. The first one, the first unexpected state was the X3872 that I just mentioned. The second unexpected was a charmed hidden state, that is a particle which decayed into J-psi plus a charged pion, which obviously could not be a charmonium. And then later on, a third unexpected set of states was discovered, in fact, in China by the Chantao factory in Beijing. And they, at this point, started filling what we thought could be a scheme to describe these hadrons that is called the tetraquark scheme. To describe these states as bound states of diquark and an anti-diquark, an idea which was introduced by Jaffe several years before. Next, this shows various interpretations of these states, which now are more or less running. One is the hadron molecule, to consider these states as bound states of QQ bar hadrons. In other words, they are like nuclei made of proton and neutron, and they instead are made of charmed mesons. Then we had our proposal of a compact diquark, anti-diquark state, and then various other variations. One very popular at some time was called the hadrocharmonium, that is essentially a charmonium surrounded by a cloud of light quarks that would neutralize in such a way that color would be neutralized. I will focus on number 2, the diquark anti-diquark scheme, and try to tell you what can we predict out of this scheme and how this compare with the observed hadrons. Next. Come back. The compact anti-diquark quark makes a firm prediction that exotic hadrons must conform complete multiplets of flavor SU3 with mass differences which are essentially determined by a scale of 130 MeV, which is the mass difference between the strange and the light quarks. And this prediction can be tested and leads to predict the unseen states, and that's one of the games that we will follow. Next. After the JPSI discovered, there have been the discovery of other exotic, which contained not only the charm meson, but also the strange meson. And the first was discovered by LACB in 2016, SAIFR resonances, that is resonances which had a charm-anti-charm pair and an S-bar pair. More recently, strange exotic hadrons have been discovered, which are called ZCS, indicating that they have hidden charm and one strange quark. In fact, BES3 discovered the one that you see on the left-hand side, called ZCS 3985, and LHCb discovered the peak that you see on the right, LHCb ZCS 4003. So you could start building SU3 octets with the exotic particle that you have. Next. Yeah, okay, go next. How can we classify these states? Well, hidden charm tetraquarks must form SU3 octets because the light quark is a QQ bar. And as you know, SU3 octets quantum number are distributed on this octet diagram. But next. But in this case, the masses of the upper and lower state are the same. And so you can also describe this with a triangle which has 3 floors. The lowest floor is the lightest, which for vector meson would be rho and omega. The next one for the vector mesons would be K star, and then the upper limit would be the phi. And you expect a pattern of masses like that also for the exotic tetraquarks. What can we say next? As I said, we have observed the X3872, which is an octet at the lightest state. And then we had observed also the 3900, which also belongs to a triangle of this kind. In 2017, we could say that there should have been a ZCS at the average mass between the 4140 and the 3872, because the 4140 is like the phi, the 3872 is like the rho, and the strange particle in between should have a mass that you can estimate 4006. And you see that the one of the LHCb states is 4003, which is not bad as a prediction. Then the other one that was found by BES3 is 3982, which is a little bit too small to have for the 39, too light for the 3900. But next, we know that there are in fact 2 Z with negative charge conjugation that I had in the really first slides, 3900 and 4020. So there must be 2 strange particles. And in fact, LHC see another ZCS at 4220. 3982 is a little bit too low for being the companion of 3900, and 4220 is a little bit too high. But these 2 octets have the same quantum number, so they can mix. Next, they can mix with each other, and the mixing with the particle at the expected level, just produced by the repulsion of the level, could produce very well the 4220 and the 3982. So I think we have 3 octets which are almost completed. What is missing? What is missing for the first octet is the companion of 3872, that is the analogous of the row. So that would make the lowest state, while for the other one, we miss also the upper state. Next one. So the shopping list is that we have to have two C bar S bar CS at the top of the triangle with rather well predicted masses. And that next, and then we have the companion of the X, which is called the X plus. Go to the next, okay. And we are able to predict the branching ratio to see these particles starting from BDK. And at the moment, there are only upper bounds to this ratio, which say that this ratio is less than 1. And so, in fact, it has not seen yet. But of course, it has to be, is one of the particles that we should find. Next slide. Okay. Now I go to another category of particles that have been found, which is very interesting, is single charm tetraquarks. That is, this exotic meson contain 1 charm and 3 light quarks. Now, it is interesting that there is a recent study on the lattice QCD, which has studied the attractions in the channel DK. Now, in SU3 flavor, the bar K is a combination of 3 irreducible representation, the 3, the 6 bar, and the 15. But the lattice gauge theory find attraction only in the 3 and 6 bar, not in the 15. Next. What happens in the tetraquark? If you have this combination of quarks, C bar, light antiquark, and 2 light quarks, the 2 light quarks, Q1, Q2, have 3 bar color, spin 0. I'm speaking of spin 0 particles, spin 0, and so they are antisymmetric in color and in spin. And therefore, the Fermi statistics tells you that they must be antisymmetric also in SU3 flavor. That is, they have to be a 3 bar of SU3 flavor, combining with the 3 bar of the anti-quark, which is together with the charm, you get 3 bar times 3 bar, which is a 3 plus 6 bar, but you don't get the 15, which is a nice result, which parallels the lattice gauge theory. This prompted us to study closely the SU3 properties of these particles. Next, and they are a 6 and a 3 bar that you see here, a triangle with the vertex up, which is the 6 bar, and the triangle with the vertex down, which is the 3, and so a complex of these states. It was possible to identify one of these states, the T3, with a particle which rather light, 2317. But next slide. In fact, well, no. Before I make this remark, that we have already seen states which contain 2 light quarks, and these are the charm baryons, which are a charm and 2 light quarks. Next step. And these are very well known as the sigma C, sigma charm, lambda charm, psi charm, and the omega charm. And they are the conjugate of they are a 6 plus 3 bar. And they also, the difference between sigma and lambda is that the sigma as belong to the 6 is symmetric in the quarks, and the lambda is antisymmetric. Next. However, sigma, the mass in this distribution increases linearly with the strangeness, and so there is a difference between the omega c and the sigma of about 270 MeV. Next. Now, what happened for our triangles? In our triangles, the top of the triangle S33 has a 3 which sorry, the bottom. The bottom of the triangle S11 has a 1 which corresponds to a U-bar quark, but the other one corresponds to 2 quarks in antisymmetric states. The top of the triangle has 3, and they have 1 quark S bar, 1 anti-quark S bar, and a couple of antisymmetric U and V quark. That means that the composition in terms of quarks of the upper and the lower states is equal masses, because they have 1 heavy and 2 light quark masses. So we expect the degenerate situation in which there is no increase in the mass going on the triangle, but the upper and the lower are equal. Next. In the Charman baryons, instead the 3 and the 1 follow the composition in terms of S and quark, and you have a triangle in which the vertex and the basis are differ by, as I said, 270 MeV. It is remarkable that the group theory can deal with both situations, both triangles, in one case giving a slope to the increasing mass, which is about 130 MeV, in the other one by predicting that the slope must be 0. Now, what happens in reality? Next slide. LHCb has discovered 3 states which can be classified as a single charm tetraquarks. But they have all the same masses. But their strangeness are such that the X0 2900 is on the top of the triangle, and the other 2 are on the bottom of the triangle. So you see that they reproduce exactly the SU3 flavor distribution that was predicted by the diquark, anti-diquark. The only states that have different masses and have not been discovered yet are the two states which are in the middle of the triangle, and they have masses which can be predicted by SU3. Go on. Next step. Yeah, this just says that these masses can be predicted. Next step. And I would say that the mass degeneracy of the X0 2900 and the 2 DS0 2900 is really interesting, because it's a real confirmation of the fact that the strangeness in the 2 cases is bring by, in one case by a strange quark, and the other case by the anti-strange quark, but they are in the same SU3 multiple. Next step.
2 more minutes, Luciano.
Yeah, I'm just about to finish. I want only to make one observation, that in the molecular interpretation, next step, give me the next one. In the molecular interpretation, the 2 light quarks, Q1 and Q2, are in 2 different, their color is not correlated. And therefore, they don't have to satisfy Fermi statistics. So this degeneracy that I found for the previous triangle would not apply to a case where the triangle is made by a molecule of DD star. Next. I have here a list of the predictions that are to be tested by experiments, but the message that I want to tell you is that we need more experiments in this region to find all the missing particles, like the old situation in the SU3 of Gell-Mann and Neyman. That means that there is still physics to be found, not only at very large energies, but also at the present energies. And this brings me to the last slide, which contains the message that I wanted to pass to you. In China, there are many discussions about future infrastructure. One of them contains the suggestion for the project for a Charm-Tau factory of of a new generation in the center of mass energy between 2 and 7 GeV and with a very high luminosity. This is discussed in China, but while preparing this talk, I was thinking to put the problem in front of you. Can we consider a construction of a super Charm-Tau factory, which is not so large, not so different from the light sources that are already existing in Latin America? Can we take that as a common Latin American experimental activity in particle physics, as it has been the case of the proton synchrotron from CERN at CERN 70 years ago? Thank you.
Thank you, Luciano. Are there any questions from outside or here?
So I have a question, Luciano. So for
Yes.
for the particles that are the generating mass, the same mass,
Yes.
how can you distinguish them in LHCb, for instance, some experiments?
What is the difference? The lowest, if I can get back to the previous slides. Can I go back? The previous one. Oh, yes. The two Ds are at the basis of the triangle, and they have isospin 1. But the top of the vertex is a isospin singlet. So this distinguishes the two, and also the top of the X2900 has a strangeness +1, and the other one has strangeness -1. So they have very well defined strangeness and isotopic spin quantum number, and they can fit perfectly in this scheme. I don't know if that solves.
Okay. And the other question is there anything that this Tau Charm factory can do that LHCb cannot do?
That's an interesting question. In principle, no, because if you have energies like that, you can pair produce the exotic mesons from photon annihilation, from E+ E- annihilation. And LHCb sees instead this particle as produced from B decay, in B decay. Now, there is a wide difference in terms of background. LHCb can have a much larger luminosity, but certainly has a much larger background, and so it's difficult. For instance, if there are particles that decay with a pi0, it's very difficult, or eta, it's very difficult to see them in LHCb. So in a way, they are complementary. One is favored because it can produce, but is unfavored by the small cross sections, and the other one is favored by large cross section, but is unfavored by a hadron background. And in fact, what we have seen over the last year was a sort of competition between the two cases. And the Z3900 has been found by BEST3 because it decays into eta C, into an eta C and that is difficult to see in proton machines. But on the other hand, for the strange particle, BESS3 and LHCb have arrived plus or minus in the same time, more or less, to discover them. So the discovery potential is similar, but one is favored by the cross sections and the other one is favored by the background.
Okay, thank you, Luciano.
Any other questions? From outside? No. I don't see any, so let's thank Luciano again.
Thank you all. Thank you very much.
And next we have Pierluigi Campana about Linux in Latin America.
Hello, can you hear me?
We can hear you, and we're ready to see your slides if you put them on.
Do you see the slides?
Yes, we can see the slides.
Okay, so first of all, let me thank the organizer for inviting me to this meeting. Somehow the title seems a bit strange, but this is the outcome of a few discussions we had at recent ICFA in Prague with Latin American colleagues, and I think this was somehow there were some hints to present this talk. So I would like to start with, as I'm ICFA chair, I would like to start presenting what is ICFA. Maybe some of you are not aware of ICFA role in the last 50 years. And the ICFA is an international organization which was created in '76, aiming to promote the international collaboration, especially in the construction and exploitation of very high energy accelerators. And so the activity of ICFA is mainly focused on having regular world meetings with major high energy physics lab directors and representatives from regional areas, and also to organize workshops to understand and to foster research and development in accelerator physics. So all large regions are represented, and also Latin America has one representative in ICFA. What is the main activity? The main activity is organized in panels, which are related to not only accelerators, but also to detectors. To a brand new panel is devoted to sustainable accelerator colliders, because the impact of our activities has to be understood and to be minimized. And then the computing is also concerned. And of course, one of the historical panel is the one devoted to develop ILC collider. Of course, ICFA is not expected to decide on which will be the next global collider, but is somehow expected to endorse projects which have reached a mature level of technical scientific definition, and also to think about a diversified research approach in various high energy physics labs. So which are the areas of global discussion within ICFA? As you can imagine, the main items are related to the governance of large project, to the impact of this, the large size of the project on our field, the problems coming from the long time span of project preparation, which includes not only the evolution of cost, but also the impact on various high energy physics, sociological aspects. And of course, also somehow to discuss about the environment in which high energy physics community is operating, especially trying to provide access to innovative technologies to a wider range of regions and countries, and coordinating this activity in regions with smaller communities. For example, at the last ICFA meeting, which was held in Prague during HECAP, we knew that we acknowledged the recent birth of a Asian high energy physics group of countries. So what is the relation of ICFA? Why this talk about ICFA and Latin America? First of all, Latin America is represented by one member at regional level in ICFA, and Gustavo is the representative. The role of this member is to report at ICFA somehow regularly the meetings on high energy physics development in the continent, and to promote initiatives like the one which we are here today among institutes in the region. So historically, Latin American high energy physics group have a large involvement in international projects, not only Fermilab at CERN, but also in other labs. And Latin American groups have strong links with high energy physics labs worldwide, with quite intensive change of people, especially young postdocs that travel abroad. And typically the activity of Latin American groups are characterized by the, I remember very well, I was working in LASF4RI. I remember very well the activity of Brazilian groups in the experiment, and imagine that this is happening also for the other activities where within the available resources, groups are taking care of responsibilities in various areas of the experiments. In general, I think here we are entering more in the key aspect of this talk. In general, for Latin American high energy physics group, it's not easy to access funds, especially if these funds have been invested outside their countries. And this is in general a more global problem, not regarding only Latin America. So we have to find a way in order to make, in order to maintain and to increase the activity of our field in Latin America, to put forward visible and relevant projects in-house, and in particular to cluster the community around them. So everybody knows very well that the role of research infrastructure is vital for each country, because the research infrastructure, especially in our field, are supporting economy and societal development. It's quite a standard to consider $1 invested in research infrastructure typically provide by a factor 3 in return to the country that is supporting the research infrastructure. And among research infrastructure, I think that accelerator-based are the one that allow for a sizable impact on society. And on top of this, of course, accelerator-based research infrastructure are somehow very, show a very big affinity with high energy physics field. So there are many, this was mentioned by Luciano, there are several synchronized sources success story. not only in Western or Far East country, but also in place a bit less obvious. We know Sirius, which is now starting with an outstanding 4th generation machine, synchronous machine, and also, for example, Sesame in Jordan, which was built in a place which is very critical nowadays by collaboration among Middle East countries, and with some difficulties is producing science and research. So this was essentially the trigger that sparked several of these kind of projects, not only in Latin America, for example, the LAMISTAR, the Great Caribbean Area machine, but also, for example, in Africa. This was quite interesting because the two projects were or are somehow exchanging, and they have interesting fallouts in the relative community, and they have also a quite strong links. Of course, this kind of enterprise, and to this I would add also the enterprise of building a charm factory, are relevant enterprises where somehow very large investment are needed. Operation cost of not only in manpower and running costs are relevant, and together with a quite relevant and long effort to approve it and to build, because especially if we are speaking of laboratories that start in a greenfield area, so you have to convince the political. You need the political endorsement. Of course, you have to choose the site, to secure funding, and not to be, and more important, to find the staff to operate it. So, but even if challenging, of course, this project fit well within the regional opportunities. For example, Latin America has the presence of a strong academic network, quite a huge amount of young generation of scientists. Many countries in Latin America have innovative emerging markets which are ready to use this kind of facility, also at industrial level, and a well-established network of cooperation with US and Europe, and of course the fact that this kind of facility has a strong application, a strong flavor in applied science, and this has a strong political appeal. And I would also say that within Latin America, also the language communication can simplify the understanding of each other. So, but given this great potential of success, we can think that in the next 1-2 decades, the possibility in the continent to have such a facility is limited to 1 or maximum 2, which do not solve at large the question for a distributed access to the community for innovative technologies. So I think that this was the subject of discussion we had with my Brazilian friends, is the explore and continue to explore complementary options, which of course engage a much lower cost scale. For example, high technology workshop for radiation detector R&D, especially in silicon-based devices, which have a great appeal nowadays, or electronics or NDAQ specialized center for fast signal and data processing. And I would add also the deployment of small-scale electronics with various applications. And somehow the rest of my talk will be focused to convince you that this is a nice way on which to go. So why Electron Linux? First of all, they are building blocks of any accelerator. It represents a very simple and consolidated technology. There is a huge amount of industrial availability of lower energy machine up to 10 MeV with a large variety of industrial systems, while at high-end energy order 100 MeV, these are more scientific oriented. There is a wide range of currents available, so intensity, electron intensity, and therefore of applications. So you have industrial application like wastewater treatment, cargo scanning, irradiation, or medical sterilization, cancer treatment, flash therapy, etc. And on top of this, as I already said, large international academic know-how and support, and also availability of spare materials. I remind you that, for example, Sesame was built using hardware coming from a previous machine. And I think it's for our communities, our typical communities, be interesting to concentrate on academic-oriented small LINACs. We are speaking, just to give the size, we are speaking of objects which are a few tens of meters long. The cost is within 20-30 million if euro or dollar. This is more or less equivalent, and with a minimal civil engineering infrastructure needed. This would lead the possibility to train technicians, engineers, and scientists, for example, for the big project, but also to make small in-house experiments at the level of university, director text, for example, etc. So this would become somehow house facility, in-home facility, which could be used widely by the community. If we make a step further, an exciting achievement development, which to my opinion can be considered as an intermediate step toward a full synchronous machine, is to get, for example, X-ray photons from an electron LINAC by Thomson scattering or inverse Compton scattering, where you run a laser in the visible against electron. So this is a very well-known effect, which you for example, you get a LINAC about 100 and you fire a 800 nanometer laser against the LINAC, and you get photons in the X-ray in the range from 20 or more. Of course, the intensity is maximum at 0 degree, and decreases as you enlarge the acceptance. But the net effect is to have a quite monochromatic spectrum at small emission angle, with, of course, the fact that you get a lower brilliance. And quasi-monochromatic X-rays are very useful. They are entering the area of application, many medical, industrial, and cultural heritage use. So you would have high resolution images, non-destructive testing, industrial inspections, high quality industrial inspection, material composition, monitoring, degradation, authentication of cultural heritage, and the study of environmental impact. For example, this is the famous papyrus, which was burnt in a fire. It was impossible to unfold, which was decoded through this technique. So I show here, sorry?
2 more minutes.
I'm at the last slide. So we have, I show here 3 examples of these opportunities. The first one here is STAR, a machine in the University of Calabria, which typically has no long tradition in accelerator domain, 12 meter long, 20 to 300 keV X-rays. Another machine in Romania, again, not a long tradition in accelerators. And this is important to underline that all this research infrastructure can be built, operated by a relatively small amount of people, of the, I would say, order of 20 people, which can be trained and supported initially, but external experts. So I come to the concluded remarks. So I try to explain what is the ICFA mandate to promote international collaboration in high energy physics, and to, more important, to try to coordinate the activities in particularly in areas where communities are smaller and a bit less organized. I think promoting science with innovative R&D and research infrastructure plays a pivotal role in the development of the country, and Latin America has all the tools to make to profit of these opportunities. Of course, there are many possibilities to develop this. Synchronous Light project represents certainly a flagship project, but I think that smaller project can be discussed and can be identified to attract resources from state, private companies, and to allow for a wider perspective of development. And LINACs, electron LINACs, are certainly a possible option for this development. Thank you very much.
Thank you, Pierluigi. There is a question from Ignacio. Go ahead, Ignacio. You're muted. Still muted.
Ciao, Pierluigi.
Ciao,
Sorry.
ragazzi.
Very interesting idea. I never heard about this kind of little electron accelerator and application, but I think it's very interesting, and I'd like to understand better what we can do about this in Latin America. But what about the proton therapy? This is more famous, and we don't have anything, I think, in the South Hemisphere.
Yes. No, you are right. I'm not an expert in this kind of synchrotron, proton synchrotron. Certainly is a much more complex installation. In fact, you have 1,000 on LINACs, you have, I think, 10 proton machines in the world. Then you have to choose if you prefer proton machine or ion machine, you know, for Bragg peak, you want to deposit in a special, but certainly proton is another option. But this has to be supported by industrial, I think, industrial companies, quite a large project. But of course, it would have a leverage on health very big. So this would be supported at many levels. You know that there are several projects around the world. For example, there is one in the Balkan area in Europe, which is called CEAST, and they are developing it. I think it's a, let's say, it's a step near a synchronous line machine, not certainly 20-30 million. You need much more complex, and there you need the help of a physician. You cannot do alone.
Okay. Thank you.
Right, we got another question here.
Yes. Sorry, this is maybe a silly question, but the Sirius must have an injector, right? Which probably injects the beam, I don't know if once or twice a day. And I was wondering, maybe it is not feasible, but is it possible in between injections to switch the beam for another application or something like that?
So I think that in principle should be possible to send a beam, for example, in a test area. This would be a nice facility for the whole continent. To, for example, if you have to test a detector of making other measurement, this would be. The problem is that typically synchrotron machine people do not want to have interference with external world because they have to run 24 hours, 7 days a week, the machine. So typically they don't want to have, they're not so they want to have the beam only for the machine, but in principle it's doable. For example, you can, I don't know the rate at which they inject, but in principle out of, I don't know, 100 hertz, you can take 2 bunches and send it to another area. One should discuss with serious people, serious machine people.
Okay, any other question? If not, let's thank Pierluigi again.
Thank you very
And
much.
Our last talk of the day is Elio Damota. He's here. He's gonna talk about liquid argon detectors.
Should I use my laptop? No, we have this presentation. So, Adam is a novel man.
Yeah.
Not a serious person. Doesn't look serious, but he's a noble man.
And in fact, the same question you have just presented, I asked them some time ago when I was there, serious in talk. The answer was pretty much the same. Of course, it's possible for them to divert part of the beam to a beam test area, but somehow they are not up to that. Okay, that's not the idea. Maybe if you want to do that, and maybe it's the only facility in Brazil, sure, the only facility in Brazil where you may expect to have an electron beam, and we should work with them and talk with them and see what can be done to achieve that goal. It's clearly possible. Oh, thank you very much. Okay. I'm really not going to talk about Dune because that's not the talk about Dune, but pretty much about what we here in Brazil, our group, are doing at Dune. And okay, so we talk about the effort that we have about the liquid argon detectors for the neutrino field. So it's not just for Dune. Dune is our flagship experiment, but it's not just about Dune. It's much more than Dune. Okay, and just to have an idea what you have, we got all the institutions in Brazil, everybody who works at Dune in Brazil, and with a group that we call Dune BR is here, but this thing, okay, it doesn't show. Okay. We call Dune BR, and we have even a page, a web page, when you have all the activities of the groups, how the developers, and we have job offers. If you look for a job, we have offer jobs there in position for students, postgraduates, and so that's what. So we call it Dune BR, and we also talk about a little bit about the Brazilian contribution. We have the SBN. The short baseline neutrino facilities experiment, not just an experiment. Over here. Okay, so we have this Brazilian effort. This is a white paper that describes the main activities and projects where Brazilian groups in neutrino program based at Fermilab. In fact, Dune is not a Fermilab experiment. Dune is supposed to be an international collaboration. Of course, the main facility will be starting at the Fermilab. But there are also things that are happening now at CERN. So it's not a CERN experiment, it's not the Fermilab experiment. This is a kind of problem because you have a kind of agreement with CERN and say, well, this is not a CERN experiment, this is not a Fermilab experiment. Depends on the convenience, it's a CERN experiment. Depends on the convenience, it's a Fermilab experiment or either of them.
It's a schizophrenic.
Okay. But anyway, they oscillate, they change a lot from. So the deep underground neutrino experiment, that's so-called Dune, and the short baseline neutrino program. Okay, Dune, what we are basically involved in Dune, there are lots of things, to just make things a little bit short. We have lots of people working with the instrumentation, and we have the Dune and Proto-Dune. Proto-Dune, as the name suggests, the prototypes for the Dune experiment, of course, and the photon detection, and the FD stands for fire detector, and fire detector phase 1, fire detector phase 2. And people here have worked very well into producing assembly what's called Arapuca for Proto-Dune. Arapuca, I'm not going to talk much about that, but it's a system that was developed for a photon detector system that has been proven to be very efficient, and it has been accepted to be implemented. But again, it's not something for Dune. It's a photon detector system that can be used in any system that in principle you have to detect the photons. And some people have been talking with people from Campinas from Brazil about using the same idea, the same technology for the process. They have also been working in the filter evaporation for Proto-Dune, and HD is the horizontal drift, and VD stands for vertical drift, because Dune has a set of detectors that they have at some point have a drift of the ions and the electron. And there are two ways of doing it. One is when they drift horizontally, the other when they drift vertically. There are some different technologies, some advanced, so they have these two possibilities and the two tests that have been done. People have been involved in that. And you have also good involvement in computing, because you need lots of computer for simulations. And of course, Dune is not running out. Dune is going to run in 2032. When I got Dune, Dune is going to run into 2022, then it was 2026, 2028, now it's 2032. Okay? But anyway, so there are lots of computers to do lots of simulations, not just for the whole Dune detector, the experiment, but also for small and parts of the detector. And to do that quite a lot. In fact, Dune has a network of computers, a global network of computers, when you have computers from several parts of the world connect together in a grid. And we are in that grid. So Brazil is the only country in Latin America that is part of the grid. The BPF grid is part of this big Dune computer system. Now, there is a new proposal for the fire detect phase 3, when people have been involved in tests. LA is that for liquid argon tests. It's very important. Liquid argon is fundamental for Dune many other experiments, because of the main core of the detector itself. So it's very important to understand how they work. Material characterization, because there are tests on the adhesion, how the PTP is a material that's the dichroic filters. Again, the Arapuca, for those who do not know, Arapuca is an Brazilian Indian word that stands for a trap. It's a trap for birds. The Indians build that, so when the bird would get there to get some food, they would activate the trap and they catch the bird. So this Arapuca, some people think that Arapuca stands for something and try to find out Arapuca is A for, it's not that, it's just the trap, okay? So it's basically a trap for photons. So when the photon gets in this, let's say it's a box, and there's a window, and the photon gets into the box, and there is some parts of the box, there is the sensor. It would be a photomultiplier or a silicon detector, doesn't matter. But the photon is not intelligent. It does not go straight to the detector. So what happens with this box is has reflective walls, and the photon keeps bouncing there until reaching the point. Well, of course, in this bouncing there, it can go bouncing back through the window. So that's why there is a trap. When they got through the window, it goes through a wavelength shifter that changes the wave of the photon in a way that it was a photon had a wavelength that allowed it to get into there. But once the wavelength was shifted, it cannot go back. So it trapped in there, and eventually became. So that increased a lot the efficiency in collecting the. So that's why it's a trap, like a bird. Okay. Liquid argon purification is very important, because the argon should be as pure as possible. And what happens is the liquid argon, Dune has a huge amount, 40,000 tons or whatever, the liquid argon. All the argon in the world has to be taken for Dune, basically. I hope so. And what happens is it has to be pure as possible. What means that you need some purification system. Okay, and so people here have been looked this, and what happens here, there was a very good program that developed an innovative process to purify liquid argon. So this was developed here. There were tests in Campinas, And they were then tested at the Fermilab, and it works very well. So it's a new technology that has been developed here. About software, well, there are lots of things that to do with software. So all these systems have to be simulated. And then we have lots of, this doesn't work. Okay, we have lots of work in the analysis. Liquid argon software is all the software that works with the argon, lots of simulation. And we also have, well, we also accept some theorists in our group. So we have people working in phenomenology. Okay. Very shortly, what this program is about, deals with the origin of matter, okay, it investigates electronic CP violation, what implies that we need a precision measurement of oscillation physics, so to know basically if the neutrinos and antineutrinos, do they oscillate the same way, so you need very precision measurement of that. And we also have work that deals with neutrino mass hierarchy. I don't know, it's the kind of the normal inverse hierarchy. There is also a possibility to work with the neutron stars and black hole formation because the detector detects the neutrinos. Does not discriminate. Does not care if the neutrino is coming from the accelerator, from the sky, whatever. So it's also sensible to neutrinos coming from neutron stars formation. So there's the ability to observe neutrinos for supernova, for instance. And if you observe the formation of black holes. Okay. Another problem to do with unification force because it can investigate the proton decays. Some people believe that proton decay, okay? So it's possible to investigate because it is a huge mass. In fact, I have a presentation that went to student when I just got a model of the Dune detector to detect and put it in Maracanã Stadium. Maracanã Stadium is the biggest soccer stadium in Brazil. And does not fit there, okay? It's a little bit bigger than the field. So it's a very good way.
What module?
No, before. The four model, they go beyond the soccer field. Okay. So it's a huge thing.
Or two, actually.
In fact, there are supposed to be four models. So anyway, it's big, huge amount of liquid argon. So it's a good place to try and investigate this proton decay. And also to work with atmospherics and solar neutrinos. As I said, it doesn't matter where the neutrinos are coming from the detector, you detect them, hopefully. Okay, very short. This is if you saw some presentation about doing somewhere, you saw this both. Okay.
Yeah, I told about this.
Yeah. Ali told.
Yes.
Okay. So anyway, so no basic, but so here's Fermilab. That's where the neutrinos will be produced. There is a proton acceleration. Then neutrinos are produced, and they go over. The very important things about this, because it works only. It doesn't work if you have a flat Earth. Okay. It's very important that the Earth is really round. Otherwise, we are doomed. Okay. So let's say that once Dune starts working, there will be a very strong evidence that the Earth is not flat. So this is very important. Nowadays, it's extremely important. Okay. But anyway, so it goes all the way about over 1,000 kilometers, all the way down to South Dakota. When there is so there are two detectors. One detector is the near detector and the far detector. Okay, without much going to mention. So this is how the detector should look like. Okay, so those are the models. And there you show one of the models called the single phase. That's a horizontal drift. And this is another one that has a vertical drift. So this one, the drift goes up, vertical, you on the horizontal. There are two different technologies. You guys do different tests. Okay, the Dune is divided in phase 1, 2, 3, 4. They're like an iPhone. Every year we have a new model of iPhone, 1, 2, 3, 4. So there is always a new phase of Dune. Okay, they describe how the beam power should be. I'm not going to say how the neutrino being introduced. That's not the point here. I guess that everybody knows how it works. So you have the far detector. It has 4 modules. The one that do not fit in the Maracanã Stadium, and a near detector. And there are the near detector has some possibilities. So there are some tests that have been done. And these tests are underway now. Much of this is simulation. Some of them just small models that they use. Dune far detector, that's the one very far away. This is just some cartoons showing how they should work. So in one point, you have the horizontal drift, in the other one, the vertical drift, the two different technologies. And you see here the Axie Arapuca is the Arapuca that I mentioned, but it's an advance of the Arapuca. So that is even more efficient than the original Arapuca X. I suggest them not to call it Arapuca, call it not X, call it Arapuca Açu, because since the Arapuca is in India, Açu in the Indian Brazilian means big. So Arapuca Açu, they did not like because there is a cess bill, and this would be too much for the American press. So they went for the more traditional X Arapuca. But anyway, it's the same thing, the same idea, but with advances that make it more efficient. And they are used in both for the horizontal drift and for the vertical drift, and they have been tested mostly at CERN. Okay. Another photo just showing how things work. And here we see several countries that are involved. Brazil is involved with the filters and the frame, because they have to make a frame for all this thing. And all the other countries involved. It's a big project. The photon detection system, that's the one that uses the Arapuca. So the vertical drift does not have because there are mechanical constraints on how to install. It's not just a question of physics. They have to be sometimes some mechanical constraints on how to build it vertically or horizontally. They have to be redesigned with a square shape for mechanical reasons, and that maximizes the light. So that's the point where simulation happened a lot. So there were a lot of simulation trying to see what geometry would produce better results before we really start doing the thing. And lots of people from Brazil are involved in all this process. Just another photo. So here you see, this is at CERN. So you will see, Protodune is not one experiment, just the Protodune is the leader of the system. Okay, the prototype of Dune. Here we have two of them. One is the horizontal drift. The other one there at the bottom is the vertical drift. Both are used, both are assembled at CERN, and that's they use it for to test it to see. But the point is that they are not just they are prototypes, but they are real detectors. So you can do some physics with them, and people have been working with it. And they have, again, the Arapucas are there. And together with the Arapuca, people here in Brazil also have developed the electronics to work with the Arapuca and the collecting data. Okay, there's more photos. People like to see this photo because this is here. This is in Campinas, so people are testing all the systems, developing and testing the Arapuca. There's a big lab there in Campinas at Unicamp. That's the lab, where they have all these facilities to develop and build and assemble the. So this is very not important. I mentioned at the beginning that the purification of argon is very important. Okay, and so they built here in Brazil. That's the cryostat. Okay, they cryostat and developed this new system using a new technique. That because the argon itself, they have to remove, say, oxygen from the argon. They have to remove nitrogen. And there at Fermilab, they have a system that's in fact not to the Fermilab that's quite efficient in removing oxygen, but it was not very good in removing nitrogen. Okay, so they developed here, with people from Campinas also, a new system with new materials that has been very efficient in removing nitrogen. So this was tested here first, and this with this very small, this is a small cryostat. Okay, this is all made in Campinas. But then once it worked, they moved it to Fermilab in a much bigger facility and much bigger cryostat there, and they have performed this test there. And Leah probably talked about it, I guess so. About software, okay, all this thing has to be simulated. Okay, the Arapuca had to be simulated. How light is collected had to be simulated. So there are several models. When you have 2 or 3 models to describe something, it means that you do not know. Because if you know, one model is enough. So they also have different models, so they have to test all of the models and lots of simulation. And that's a kind of thing that you see there are several universities. UFABC is a federal university. ITA is a federal institute. Another university, TFPR, and another university, Unifesp, all in São Paulo. So they have been using the facility, the computing, the network to make all the simulations that they have been produced good result. Okay, the SBND, the other part, this is the standard for short baseline neutrino detector. It's a baseline aligned with FEMLab. There's several experiments. There is microboom, you have SBND, and have Icarus. And right now we are in the process of joining Icarus. So we have people here already working at SNBD, and now we are going to join Icarus. So but people have already made the contribution SS and SBND. I'm not very good with this. SBND. And in fact, they had the collaboration meeting was here in this very same facility last year, November or October, something like that. The collaboration meeting was here. So there have been lots of contribution from Brazil, like the production, assembly, installation tax, again, tax Arapuca system there. So not they doing, but they are really working there as PND. And the evaporation of the correct field. The correct filters in that the Arapuca that I mentioned, that's what makes the trick. Okay, that's the when the photon they are there, they have to the correct field. They are sensible to some wavelengths, not the other, so they change. So, but they have to test how the correct filters work because they're subject to temperature, to pressure. So they have lots of work doing that. And they developed the Apsaya and Arara and readout electrons. As I said, they had also developed the electronics. So Arara, for those who don't know, is a macaw, it's a bird. Okay. Apsaya is nothing. She said a real, but Arara is a bird. Okay, so they have developed it and they have to test and test it here, test it there. And of course, the simulation data acquisition. Again, more photos are here in this photo. 2 minutes. I have lots of things to say.
Three.
Okay. Okay. So this is another photo. Here you have a vision of the module. So PD is photon detector box, the box away and the photon detector that they installed. And there you have a view of the big thing there. The photon detector box in the big TPC. TPC is the big chamber what to detect. Here to the right again, I have the photon detector system, the back system. Here you see those boxes here. So all these things are made from the Arapucas that are installed and working there. This is at CERN. Now a list of names. We start with the most important people, go down to those with less importance. Okay, so then here you see all the institutions involved. So CBPF is involved, Unicamp, as you said, lots of people from Unicamp. We have the University Federal São Carlos, that's another federal university, ABC, ITA, that is Federal Institution I mentioned, National Astrophysical Laboratory, all the universities from Minas Gerais. So we have a total of 10 institutions from Brazil involved there. It's a good number of people. So a disclaimer, this was the last minute presentation. We have to do it very fast because Rogério came to us and basically forced us to come here and made a presentation. So we have to do this very, very fast. Just put things together very well. And the white paper that you got is incomplete. That we know is incomplete, but we told Rogério that we are going to improve it, and he believed. So, but anyway, I hope this gives some presentation showing what Brazil has been doing there, and we have been doing a lot, I think. We have a very good participation. It is recognized. I think the LIA made that very clear. Okay, and just to say that's not just DUN. Okay, DUN is the flagship. But that brings lots of things. So if you have an experiment, you also need a photon detection, and you should talk to people from Arapuca because it's really a very efficient system, much more efficient than the system that have been used. So that's it. I cannot go ahead.
Questions for Elio?
So if you have a big box and there's a small window, is it difficult for the light to go in?
What do we need to go?
It has to go exactly.
I don't know exactly. Yes, I don't know exactly how the things done, but of course, the big detector, light, has many modules. Maybe, as you said, maybe some tubes or that produce the light, like the liquid argon, and then at some point the light is colored. Right? If this is big, doesn't really matter. The point, if you don't have the Arapuca, for instance, you're going to have a photon multiplier or a silicon detector at that point. Okay, this basically does not change. Okay, we still have the detector, but but the detector is not just connect straight to the line of the, it has to connect to this box, and the box of the shape can change. I do not know if this is exactly what we want.
The point is that the window is big, right? Because it is one side is open for the light to enter.
The one side has a window, right?
So once it enters, it may be reflected. If you don't put the decorative field, it can go back.
Yeah.
So the idea is it first passes the decorative field, then there is the wavelength shifter. Once they shift the wavelength is shifted, then the decorative filter is blocking from going back. And so you have a large window for accepting, but the light cannot go back.
But I think the size of the thing people have simulated it, so probably there is an optimal size, but I. Walker side.
Another question from Jose?
During the lifetime of the experiment, I think you cannot intervene into the detector, right? So you need to make sure that electronics, etc., can survive.
But it's the same for each and every experiment. In fact, with neutrino experiments is not that critical because you can really get close to the neutrinos. At the very moment, there's zillions of neutrinos going through your body. Right? Nothing really happens. So you think that in fact you can go to the detector and replace it, but that's the same with each and every experiment in high energy physics. Sometimes some channels stop working. Okay, that's okay. We'll go like that. Well, then when you have a chance to go there, replace them. The problem with the liquid, maybe the biggest problem is that we have this huge amount of argon that you have to purify. And here the lab with Campinas, they have a small cryostat. At Fermilab, there's a much bigger one, but that's not even get close to the one at 40,000 ton, whatever you do. So, but yeah, it's possible to get any replace thing. No, that's really not a problem with neutrinos. You cannot do that at CMAS. You cannot go there when things are working.
That's worse. Yeah.
Yeah, but anyway, but that's a problem where each and every
But
experiment.
this would require you to remove the liquid area?
No. The decision is such that this liquid argon, let's say, the filter, that's what it does, that it removes the nitrogen. Of course, it gets saturated at some time. Then you have to remove this filter from there and clean it. There's a process of cleaning and then put it back. So the system is designed the way that you do not have to disassemble everything. So you just move the piece out and make the cleaning. That's basically heating up a little bit. And everything, when it is restored, you put it back. And in the way such that the argon breaks there. I do not have this here, but they have plots showing how the purity improves in the argon with time, 1 day to day. So at some point it saturates and you have to do it again. It's related. Of course, this thing with the 40,000 is a big thing. So everything is big too. It's not. And it's going as they have to scale up from this small detectors to the big one. But they are working on it.
Okay. Any last question from outside or here? If not, let's thank you again. This is it for the day. Thank you very much for everyone.
Long day.
Are you going to do?
No, I'm going to do it. The days are getting long.
I have this.
Getting shorter. No,
Obrigado, Hélio.
Nada, tchau. Manda um cheque depois.
Vocês têm 40 milhões de